Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on calculus of variations, lecture number 5, in which I will solve the catenary problem with the help of calculus of variations. Now we solve a problem. This problem is generally known as catenary problem in calculus of variations. There may be many type of questions referred to this problem. Question is, use the calculus of variations to determine the location of a uniform string of given length with fixed end points under the influence of gravity, or investigate the extremum of the functional integration limit x0 to x1 y under root 1 plus y prime square dx, provided integration limit x0 to x1 square root 1 plus y prime square dx equal to L be the constant, or find the form of an absolutely flexible, non-extensible, homogeneous rope of length L suspended from 2 points A and B on the same horizontal line. Now we solve this problem. Let AB be a given string of length L. The endpoints A and B are fixed. Let the coordinates of A and B be x0, y0 and x1, y1 respectively. The shape of the string is a curve under the influence of gravity. Let G, coordinate x bar, y bar, be the center of gravity of the string. Let ds be the elementary length of the piece of the curve. Therefore, x bar equal to integration x ds by integration ds, and y bar equal to integration y ds by integration ds. Let this is number 1, this is number 2. Since ds square equal to dx square plus dy square implies that ds by dx whole square dividing both sides by dx square. This is 1 plus dy by dx whole square implies that ds by dx equal to square root 1 plus dy by dx is y prime square, implies that ds equal to square root 1 plus y prime square dx, taking integration both sides, limit x naught to x1, limit x naught to x1, implies that this is s equal to integration limit x naught to x1 square root 1 plus y prime square dx. Since length of the curve is L, this is L given and this is constant. Let this is number 3 and this is number 4. Since in equilibrium position the center of gravity G of the string occupies the lowest position, means height of the G from x-axis is lowest and this value is y bar, that is the value of y bar is minimum, implies that from 2 integration y ds is minimum. Y bar here, y bar equal to integration y ds by integration ds. So numerator will be minimum, then value of y bar will be minimum. This is number 5. Taking the value of ds from 3 and using in 5 we get integration y ds equal to square root 1 plus y prime square dx is minimum. We may use minimum limit is x naught and maximum limit is x1. This is number 6. Now our task is to find the extremum value of integration y square root 1 plus y prime square dx x naught to x. For this we use the idea of isoparametric problem by taking help of 4 here. Therefore, we will find the extremum value of, firstly we take this function y square root 1 plus y prime square plus lambda integrand part of 4 square root 1 plus y prime square dx integration limit x naught to x1. This will be equal to integration limit x naught to x1. We take common square root 1 plus y prime square. Here remains y, here remains lambda dx. Let this is I, this is number 7. Let function of y and y prime equal to y plus lambda multiply square root 1 plus y prime square. This is number 8. Using 8 in 7 we get I equal to integration limit x naught to x1 f y prime dx. Let this is number 9. Since f does not contain x, therefore Euler's condition for extremum value of I will be f equal to c plus y prime partial derivative of f with respect to y prime implies that f minus y prime partial derivative of f with respect to y prime equal to c. Let this is number 10. Using 8 in 10 we get f is this y plus lambda square root 1 plus y prime square minus y prime partial derivative of f with respect to y prime. This is treated as constant y plus lambda. We are differentiating partially with respect to y prime. So this will be 1 by 2 square root 1 plus y prime square multiply 2 y prime, and this equal to c. Here 2 cancel. Here we take common y plus lambda remains square root 1 plus y prime square minus y prime multiply y prime square by square root 1 plus y prime square, and this will be equal to c. Implies that y plus lambda, here LCM 1 plus y prime square, here y plus y prime square multiplication of this minus y prime square. This equal to c. This is square root, implies that y plus lambda. Here y prime square cancel, only remains 1 by square root 1 plus y prime square equal to c, implies that y plus lambda equal to c square root 1 plus y prime square. Let this is number 11. Let y prime equal to sine h hyperbolic t. This is number 12. Putting this value in 11, we get y plus lambda equal to c square root 1 plus sine hyperbolic square t, implies that y plus lambda equal to c square root, this is cos hyperbolic square t, implies that y plus lambda equal to c cos hyperbolic t. This is number 13. Implies that dy equal to, this is constant lambda, here c sine hyperbolic t dt. This is number 14. From 12, dy by dx equal to sine hyperbolic t, implies that dy equal to sine hyperbolic t dx. This is number 15. Left side of 14 and 15 are equal. Therefore, right side will be equal. Therefore, from 15, sine hyperbolic t dx equal to here c sine hyperbolic t dt. Here both sides sine hyperbolic t, so we may write dx equal to c dt. Integrating, we get x plus c1. c1 is the constant of integration, equal to ct. c1 be the constant of integration, implies that t equal to x plus c1 by c. Let this is number 16. Using 16 in 13, we get here 13 y plus lambda equal to c cos hyperbolic. Here t, value of t is x plus c1 by c. This is number 17. The constants can be determined from initial conditions. It is clear that 17 represents a catenary. Therefore, the shape of the string will be a catenary. Therefore, our problem is solved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.